Hi everyone. As we go through our work this week, what we're going to be working on is how to find the exact value of an integral. So if you remember, when we started this chapter, we were able to find exact values of integrals for only specific functions where we could use geometry formulas. And then we learned that we could use rectangles to estimate the area between a curve and the x-axis, or in other words, to estimate the value of an integral. So the big idea from that whole estimation procedure we did using our MRAM, LRAM, and RRAM, and then our trapezoids, the big idea that came out of that in that Desmos activity, if you think back, was that if we divided our area into enough rectangles, we could get really close to an exact answer, right? So the more rectangles we had, the closer we got to that exact answer. And so we're going to look at some different notation here, what's called summation notation. And you've probably seen this before. So hopefully this big kind of thing that looks like an E looks familiar. That's called, it's a Greek letter called sigma, right? And we use that for a sum when we want to add a bunch of things together. And so what we're thinking of here is adding up those rectangles. Now, we said here if we add enough rectangles, right? Really what we need to think of is adding up an infinite number of rectangles. So you can see here we're using this limit as n approaches infinity to represent that infinite number of rectangles. So this sigma is used to express the idea of adding up. And again, we're adding up an infinite number of rectangles. Now, in our notation, right, we have this f of x, right? That's indicating the y values or the heights of the rectangles. Okay. Now here, this delta x, the change in x, is representing the base of the rectangle. What is the width of that base? And obviously, if we think of dividing this up into an infinite number of rectangles, that's going to be a really, really small number, a really small change in x. And then just like we said before, right, this is just giving us the interval. It's telling us the starting value of x and our ending x value. So it's just telling us what is the interval that we're dividing up into all these rectangles. So this is how we use summation notation to represent adding up an infinite number of rectangles to find the area between a curve and the x-axis. Now, you might be wondering what we need to be able to do with that. And what we need to be able to do is express this same thing using integral notation. So everything we're about to write, these are just equivalent statements. They're just represented using different notation. So now, when we go to integral notation, instead of using our sigma here, we're going to use our symbol for an integral. Right? And you can kind of think of this as an S. So we're summing up all of these rectangles. Now, the bounds of that integral come from this interval here. So I'm going to take the integral from a to b. Now, my function here is going to stay the same. So f of x. And now what was delta x here becomes our dx in our integral notation. So these two things mean the same thing. Again, the idea being that if we were able to sum up an infinite number of rectangles, that would be giving us the integral from a to b of f of x dx, adding up all those rectangles to get the area between the curve and the x-axis. So here's what you'll need to be able to do with this. On the AP test, they may give you a question, right, expressed in summation notation, and you need to be able to express that as an integral. So basically translating between the summation notation and the integral notation. So here's how this is going to work. We know we want an integral, so we start with that. Now I'm looking for the bounds. And remember, we said the bounds come from the interval that they're going to give you in the problem. So in this case, my interval is from -1 to 3. Now, I have to look for my function, right? And we know that comes from here. But this looks a little strange. You'll notice I have these m sub k's here. When we're talking about adding up rectangles, these might have, say we were doing a midpoint approximation. So we might be saying this is the midpoint of, let's say, the first rectangle or the midpoint of the second rectangle. But when we change to integral notation, those m sub k's, or you'll see in the next example that's a c sub k, those are just our x's in integral notation. So wherever I see that m sub k, that just becomes an x. So my function in this case is 3x squared minus 3x plus 5. And now I'm almost done, but remember back, we said the integral is always closed with a dx, or whatever that independent variable is. So now in this case, my delta x just becomes my dx at the end. So that's how we would switch between summation and integral notation. So we're just going to do one more of those. Again, it's saying to express it as an integral. So I know I have an integral. Now I'm looking for that interval. They give that to me as 0 to 1. Now I'm looking here for my function. Whoops, there we go. And again, that c sub k, remember, for us is just our x. So I have the square root. Everything else stays the same. 4 minus x, and that was squared. And then the last piece is my delta x, which becomes my dx in the integral. Okay, so the big idea there is just realizing that these two things mean the same things. We're just talking about adding up kind of that infinite number of rectangles so that if we were able to do so, we would get the exact value of the area under that curve. All right, so now before we jump into this idea that we have at the top here, these antiderivatives, I want to talk a little bit about derivatives first. So we're going to do a quick review, and we've got some nice easy problems here. So my directions say just to find the derivative of the following functions. So I'm going to go ahead and do that. So for number 1, I'll get f prime of x equals, this is just a nice polynomial function, so I'm just going to use my power rule, which is 2x plus 3. All right, I don't have a third term because I know the derivative of that constant is 0, so it just kind of disappears if you want to think of it that way from the derivative. Okay, number 2 is f prime of x equals 2x plus 3. And so here's what I want you to notice. These two functions have the same derivative, even though they weren't exactly the same to start. Right? But the key here is they just differed by a constant. So I'm going to make a note that f of x differs by a constant. Right? So we have two different functions that differ by a constant, but we get the same derivative. Same thing's going to happen down here. If my function is sine of x plus 8, my derivative is going to be cosine of x. Again, that 8 is going to drop out because its derivative is 0. Over here, again, I have cosine of x because that constant term drops out. So even though my functions differed by a constant, they're going to have the same derivative. And so that's going to be really important coming up here with what we're going to talk about on the next page. Now don't forget, this should actually be the extra page that I handed out. The page in your book had some typos, so we just printed you a new notes page. All right, so the big idea here that we're going to talk about today, and that's going to get us closer to being able to calculate these exact integrals, is what is an antiderivative and how do we find it? So what is an antiderivative? It's just a term we use, a word we use, to describe the reverse process of taking a derivative. So in other words, now we want to go backwards. Instead of finding or having a function and finding a derivative, we want to start with a derivative and see if we can tell what the original function was. Now, you worked through this a bit in your investigation today. So the idea here, well, let's go through this. It says if f of x equals x cubed plus 8, then f prime of x, well, we would use the power rule, is 3x squared. Now, if f prime of x equals 3x squared, then the antiderivative f of x, and again, this is what you probably saw in that investigation, that antiderivative is x cubed, but I have to put a plus c to represent the constant that was in my original function. Okay, so what does that plus c mean? So if we look at the review examples, right, we'll notice that the constant term always disappears in the derivative. So when we say that, we mean back here, right, just what we talked about. When we found these derivatives, the derivative of the constant is 0, so we didn't have that term anymore in our derivative. So this is because the derivative of a constant is always 0. So this means we can't determine the value of the constant just by looking at the derivative. So we write plus c as a placeholder for this unknown constant value. So in other words, I can only get kind of so close to figuring out what that original function was, but I can't be sure what this constant value was, if any. So we put that in as a placeholder. So now, a lot of this that we're going to talk about, you may have kind of worked through in your investigation. We just want to formalize these antiderivative rules, because it's going to be really important that these, kind of like the derivative rules, these should be fairly automatic. If they're not, you're going to have kind of more of a struggle as we go through these problems. All right, so when we're working with a constant function, right, the idea here is that we're really I'm getting ahead of myself. So for constant functions, if f prime of x equals k, then our antiderivative, f of x, equals k times x plus c. There's that plus c that's just always going to be there. So I have my same constant, but I added the x term. Right, so let's take a look at this. My example is if f prime of x equals 8, then my antiderivative of f of x equals 8x plus c. Right? If I check that, I can really easily verify that that's correct. If I take my function f prime of x, well, the derivative of 8x is just the constant 8. This is a constant, so its derivative is 0. So I can check that I match my derivative. So this would be my antiderivative here, 8x plus c. So in general, if I have a constant function, my antiderivative is going to be that constant times x plus c. Okay, for polynomial functions, the big idea here is that we're just undoing, it's a little messy, undoing the power rule. So let's say I have a derivative f prime of x equals a times x to the n. So let's think of what we would have to do. When we take the derivative, we subtract 1 from the exponent, and then we multiply our coefficient by that exponent. So I have to undo that, so I'm going to go backwards. So let's see, if I have f of x, I'm going to start with this here. So I've got my x. Instead of subtracting 1 like I do with the derivative, I need to add 1 to that exponent. So instead of n, that becomes n plus 1. Now I still have my a out front, but again, instead of multiplying by that new exponent, I'm going to divide by that. So I have a over n plus 1 times x to the n plus 1 plus c. Okay, so let's look at an example. If my derivative is f of prime of x equals 4x squared, my antiderivative, I'm going to start here. So I have x. Well, 2 plus 1 gives me 3, so x cubed. Now I had my 4, and I'm going to divide by that exponent. Right? Notice this n plus 1 is what I'm dividing by here. In this case, my new exponent became 3 because I added 1, so I had to divide by 3 here. And then I always put my plus c. Again, you can easily check if you found the correct antiderivative, because if I differentiate this, it better match what I started with. So if I do f prime of x, well, now I'm using my derivative process, so I'm going to multiply by my exponent. Those 3's are going to cancel, and I'm going to get 4x. I'm going to subtract 1, and I get 4x squared, which matches what I wanted. All right, now this is probably where the most kind of mistakes get made here, is with this powers of -1. So here's what people want to do. They look at this problem and they say f prime of x equals 1 over x. Well, I know 1 over x is just the same as x to the -1. So they say, oh, I'm just going to use this process to undo that. So then they say, well, if I add 1 to my exponent, I get x to the 0. And then I have to divide by 0, and you can pretty quickly see that some things go wrong here. So we can't use that process. But here's what I want you to think about. When we're finding an antiderivative, we're asking ourselves, what function would have this derivative? And hopefully this should look familiar, right? I know the function natural log has a derivative of 1 over x. So my antiderivative equals the natural log of the absolute value of x plus c. Now that absolute value is important because we know natural log can't take negative numbers as an input. So this one we have to be really careful about. That's when we should recognize we know it's the derivative of natural log. So now my example, if f prime of x equals 3 over x, well, I know that's just 3 times 1 over x. So now my antiderivative is going to be f of x equals 3 times the natural log of the absolute value of x plus c. So those are probably kind of the 3 trickiest cases to remember. We're going to cruise through some more antiderivatives here. And again, these should be pretty easy so long as you really had your derivatives memorized well. If that's the case, then this is just going backwards. So let's kind of cruise through some here with our trig functions. Right? If f prime of x equals sine x, again, what I'm asking myself then is which function has a derivative of sine x? So my antiderivative here, now I have to be a little bit careful. I know that cosine x is going to give me sine, but if I differentiated cosine x, I would actually get a negative sine x. So this has to be a negative cosine x in front, and then I have my plus c. Okay, again, if my derivative is cosine x, I'm asking which function has a derivative of cosine, and I know that function is sine of x. Plus c, we're always putting that plus c. Okay, secant squared x, I know tangent x has a derivative of secant squared x, so my antiderivative is f of x equals tangent of x plus c. Okay, here, secant x, tangent x, that has to be secant of x plus c. Cosecant, cotangent, let's see, I know that has to be related to cosecant of x. Now, if I took the derivative of cosecant of x, I would get the opposite cosecant x, cotangent x for my derivative. So since this is positive, this has to be a negative, and I add my plus c. Lastly here, the derivative, well, if it's cosecant squared, I know that comes from cotangent of x. But again, the derivative of cotangent would give me a negative cosecant squared x. Since this is positive, I need to put that negative here. Okay, let's go ahead and keep cruising through a few more. Then we'll try one example together, and then you'll have lots of opportunities to practice this. Okay, here we go. For e to the x, the antiderivative is just e to the x plus c. If it's 1 over x, we talked about this one. It's the natural log of the absolute value of x plus c. If I have 3 to the x, this one's a little tricky. I know I'm going to have 3 to the x in my antiderivative. Now, if I were to take the derivative of 3 to the x, so if I thought this was my antiderivative, I'm going to check. The derivative of 3 to the x is 3 to the x times the natural log of 3. Since I don't have that natural log here, I have to divide here. So my derivative, or my antiderivative, excuse me, is 3 to the x over natural log of 3 plus c. Okay, and then for this one, I know this is my log derivative. So the antiderivative here has to be log base 3 of x plus c. So if I were to differentiate this, I know I get 1 over x times the natural log of the base there, which is 3. Again, these two, if these are tricky, then you need to go back and really firm up the derivatives for your logarithmic and exponential functions. Inverse trig, hopefully these should be pretty familiar. You should recognize these derivatives pretty easily. So here, this is my antiderivative has to be inverse sine of x plus c. Here I've got my inverse tangent of x plus c, and this is my inverse secant. Now, since these are all the opposites, right, they have to be all my co-functions. So my antiderivative is inverse cosine of x plus c, inverse cotangent of x plus c, and inverse cosecant of x plus c. All right, so one quick example, right, asks us to find the antiderivative of the following functions. Now, I can see here I've got 4 terms. Right, I've got that guy, I've got this guy, my secant squared x term, and then this term here. So to find the antiderivative, I'm just going to find the antiderivative of each term. So let's go ahead and do this. Luckily, e to the x is an easy one, so the antiderivative of that first term is just 3e to the x. Now, 5x to the 1/2. Here we have to be a little careful. So first I'm going to deal with this exponent. I have x. Now, I'm going to add 1 to that exponent. So that's the same as adding 2 halves. So I'm going to have x to the 3/2. Now, we said we need to divide by that new exponent. Since it's a fraction, I know that dividing by a fraction is the same as multiplying by a reciprocal, so that's how I'm going to represent it here. See, secant squared of x, I know secant squared is the derivative of tangent of x. And then, let's see, this negative 1 over 1 plus x squared, that I know is the derivative of my inverse cotangent of x, and at the end I put my plus c. Now I'm going to do one little extra step here to simplify. So I have 3e to the x minus, this is going to be a 10/3 x to the 3/2 plus 1/2 tangent of x plus inverse cotangent of x plus c. Now, it says check yourself here. I actually like to kind of do the check under it so I can keep my terms lined up. Remember, if this is my function, to check myself, I should be able to take the derivative and it should match with the original problem. So we're going to do that right here. So f prime of x, well, the derivative of 3 times e to the x is just 3 times the derivative of e to the x, which is just e to the x. Now here, I'm going to use my power rule. Again, we're differentiating now. So now I'm multiplying my 3/2 times 10/3. I have x, and I'm subtracting 1 from the exponent, so I get 1/2. Plus the derivative of 1/2 tangent x is 1/2 times the derivative of tangent x, which is secant squared of x, plus the derivative of inverse cotangent of x, which I know is negative 1 over 1 plus x squared, and the derivative of my constant term is 0. So with some simplification, I get 3e to the x. These 3's cancel, and 10 divided by 2 is 5x to the 1/2, plus 1/2 secant squared of x minus 1 over 1 plus x squared. And if I compare that to my original, I can see that I was right. Now, keep in mind, we were looking for the antiderivative. So this is the answer to the problem with the plus c. This was just to check, is the derivative actually equal to what I was looking for? Okay, so I know there was a lot in here, so then when you come into class tomorrow, you're just going to be practicing with a lot of these antiderivatives to make sure that you can do that pretty painlessly. All right, thanks for hanging in with a longer video. I will see you tomorrow.